Okay, so binary tree insert and deletion and retrieval is pretty easy actually. It's because you can use recursion. So um, anyway, so let's get started. So let's say you have a tree and this is your root node and you have a left and a right subtree or child node or whatever. Well, since a binary search tree is always ordered in this form, for example, now let's say you wanted to add 5 to this tree. Well, you know that you would have to add it somewhere here because 5 is bigger than 3 and 5 is bigger than 4. So using that logic, when you add an item, you simply have to check whether this new item is new item bigger than the root. Well, if it is, then you just add it into the left tree. Otherwise, so otherwise, well, if it's not bigger than, it must be smaller than. And you can, I guess, put an equals here. It depends on how you want to make it. It into the right tree, subtree. Okay, so this would be the recursive part. Okay, so I'm just gonna add a new page. Okay, so let's write a method for that then. Insert item, and you would have to specify a tree node, and of course your item, which is of type T for this tree. Well, if node equals null, then you can simply set node to this new item. Otherwise, you're not at a leaf yet. So this is because if you traverse a tree, eventually you'll end up at a leaf, meaning it's null, like this one right here, for example. And if you're there, well then you can just set that leaf equal to the new item. Otherwise, you're not done traversing the tree. Now, if you're not at a leaf yet, well then you have to continue traversing, which is when the logic from the previous slide comes in, saying that if your item is smaller than the root or our node coming from up here, if this is smaller than, that means that it has to go to the left, right? So we're going to insert it. Going to make a recursive call to node, and I'm going to delete this. Just 1 second. Dot left child item. Otherwise, and we'll just put another equals here, I guess. If you putting an equals here is really, or equals to is really up to the programmer, where they want items to go that are equal to the root, or whether they want to replace it, or they could, simply leave this out and make a special case that's saying, well, if the item is equal to the node, then it's a duplicate, so you don't put it anywhere at all. So let's say you wanted to ensure that there are no duplicates. Well, you would simply say this. Okay, and then there's no if statement for when they're equal to, meaning that if they're equal, nothing happens. And that's pretty much the code for adding a new item into a tree. So now we're going to look at code from assignment 5, and I'll try to line this up properly. So this is from assignment 5, which was the tree assignment. And here you can see, so if the node t-node, if these two are equal, or if the node is null, then you just simply add that new thing. Otherwise, so this is getting the item from the node for comparison's sake. Otherwise, you do your comparison. So if the key of the new item is bigger than the key of the node, then, or smaller than, sorry, then the left child of the node is set equal to the new tree with the new item inserted into it. Okay, so again, this simply means that we're setting the node's left child, equal to a new tree with the new item inserted. Okay, and this is the recursive part. Otherwise, the right child is equal to the new tree with the item inserted. Okay, and so this is done like this because then you can return the item and the entire tree, which would allow you to use a little bit of encapsulation like this, where you don't have to specify the tree, and this just, as I said, is encapsulation. Okay, so that's addition.